Hi, it's Dr. Harris with part two of our slideshows on probability, chapter three in Math 111. In this slideshow, we're going to introduce the notion of what we call a random variable and look at probability distributions of random variables, as well as expected value and standard deviation of random variables. So let's get going. So here is what we mean by the term random variable. Pretty pretty simple definition, but we'll try to look at some examples to help us understand it. It's a number whose value depends on the outcome of a random process. In our last slideshow, we defined a random process as an experiment whose outcome for any one run of the experiment can't be predicted in advance, but for which overall there's a pattern to the set of outcomes if you repeat the experiment over and over and over again. So if we're able to assign a number to the outcome of a random process, we get what's called a random variable. Here are a few examples. We're back to flipping a coin 3 times and counting the number of heads. X is a random variable. It'll be either 0, 1, 2, or 3 heads. So we get a numerical value associated with the outcome of a random process. We can roll a single 6-sided die. Let's think this is an example we're going to look at throughout this slideshow. Roll a 6-sided die one time. If you roll a 6, you win $10. But if you roll anything but a 6, you're going to lose $1. So it's essentially you pay $1 to roll the die. If you get a 6, you get $10 back. And so Y is going to be how much you win in a single play, a single roll of the die. It's a random variable. You don't know in advance which one you're going to get, but you'll either get it $10 or you'll lose $1. Another example, pick a person at random from the population, measure their height. Since you don't know what the number you're going to get for the height is going to be before the person is chosen, you're getting a numerical value associated with the outcome of a random process. That's a random variable. And the last example we're going to introduce at this moment is a pretty important one because it helps us focus on actually the study of statistics a little bit later on in the course. Suppose that you took a random sample of 25 people. Maybe you're measuring their heights, but you're taking some numerical measurement from these 25 people, and you calculate the mean response of those 25 individuals. Because you didn't know which 25 individuals you were going to pick ahead of time, that's your random process, is picking the 25 people, and you're gathering a number from each of them, and then you're calculating the mean of those 25 numbers. That sample mean is a random variable. It depended on the individuals that you chose, and they were chosen randomly. So keep that in mind. We'll be talking about sample means, sample proportions. We want to think about those as random variables, and so they're going to obey some of the things that we're going to be talking about in these next few slideshows. So now that we've got hopefully a little bit of a feel for what a random variable is, let's introduce the notion of probability distribution. And so the big picture here is that we're trying to understand, for given values of the random variable, can we assign the probability that those values are taken on? And if we're able to do that for all the values of the random variable, then we're saying that we know what the probability distribution of the random variable is. And so just to be a little bit more formal, a probability distribution for a random variable is a listing of all the possible values of that random variable along with each value's associated probability. So in some sense, it's a table where we can list all the values out and then list with them their associated probabilities. We'll do a couple of examples here. We like to think about the flipping a coin 3 times. In our last slideshow, we went and listed all these equally likely outcomes, these eight possible sequences of heads and tails. And our random variable, as we saw a few slides ago, is going to be the number of heads that were flipped. We've commented that X can be 0, 1, 2, or 3. In fact, that's initially how we really thought about this random process before we broke it down into the 8 possible sequences. So we're going to go back now and think about the number of heads as an outcome of this these flips. And for each of these 8 outcomes, we can list the associated value of x. So TTT, the value of x is 0. If I come down here, a few rows, HTH, I count 2 heads, that gets assigned a value of 2 for x. So for each of these 8 equally likely outcomes, we can assign a value of x to them. And once we've done that, we can actually calculate the probability that x will take on any particular value. So for instance, the probability that x is going to be 0, well, out of the 8 equally likely outcomes, only one of them is x takes on the value of 0, so the probability that x is going to be equal to 0 is going to be 1/8. The probability that x is 1, well, 3 of the outcomes, we've commented on this sort of thing before, but maybe not quite in such a formal way. 3 of the outcomes, TTH, THT, and HTT, have a value of x of 1 associated with them. And so the probability that x is going to be equal to 1 will be 3 out of 8. And so we see that in our table in the next slide. So the probability, we read this piece right here, the probability that x is equal to little x is the probability that our random variable is going to take on a particular value. And so if little x can be 0, 1, 2, or 3, we read this table as saying the probability that x is equal to 0 is 1/8. The probability that x is equal to 2 is 3/8, etc. So this is a probability distribution for x. It lists the values of x along with their associated probabilities. We could draw a histogram essentially of this distribution, where this height is 0.125, that's 1/8 in decimal form, and this height here is 0.375, 3/8 in decimal form. And so we can see the shape of the distribution, where 1 and 2 are each 3 times more likely than either 0 or 3. So some important properties of a probability distribution: individual outcomes, individual values of the random variable are mutually exclusive. You can't have x take on the value 0 and 1 simultaneously. For example, in this example, it can't take on the value of 2 or 1 simultaneously. X can only be one number at a time. Probabilities assigned are always going to be between 0 and 1. And the sum of the probabilities has to be 1 because x is going to take on one of those values. And so the probabilities have to add up to 1. And that comes from the mutual exclusivity, as well as the fact that one of the values must happen. So once we have the probability distribution, we can answer somewhat more complicated questions involving probability. For example, what's the probability that x is less than or equal to 2? Well, x less than or equal to 2 in this particular example means that x was either 0, 1, or 2. And so we would add, using the fact that individual values of x are mutually exclusive, we can just add the probabilities together, and we would add 1/8 for the probability that x is equal to 0, plus 3/8 the probability that x is equal to 1, plus 3/8 the probability that x is equal to 2, and we would get 7/8. Here's a picture of that from the histogram, probability histogram. If we wanted to ask instead, what's the probability that x is less than 2, instead of less than or equal to 2, then x less than 2 means that x is equal to 0 or 1. We answered this question in a different form in the last slideshow, but the probability that x is equal to 0 plus the probability that x is equal to 1 is going to be 1/8 plus 3/8, or 1/2. And here's that picture. So we want to keep in mind that we can ask questions about what's the probability that a random variable takes on a range of values simply by adding the probabilities of all the probabilities that x can take on the values that are in that range. Go back to our other example, a random variable where we win $10 if we roll a 6 on a 6-sided die and we lose $1 otherwise. Let's think about what the probability distribution for that random variable is. Well, what are the possible values of y? How much can you win? Well, clearly you can win $10. That's a possibility. And you can lose $1, which actually means that y can be -1. So y can either be -1 or 10. How often will you win $10? Well, whenever you roll a 6, 6 is one of the 6 possibilities on a 6-sided die. If it's fair, then the probability of rolling a 6 is 1/6. So in our table, we'll list y equals 10, and the probability that y is equal to 10 will be 1/6. What's the probability of losing a dollar? Well, if you don't win, you lose. So the probability of losing is going to be 5/6. And so for the value of -1, our probability is going to be 5/6. And that's what we see in this table on the next slide. Y can be either -1 or 10. The associated probabilities are 5/6 and 1/6. Next, let's talk about expected value. And by expected value, we mean what's the average value? If I repeated this random process over and over and over again, and it collected all the values that the random variable took on over those repeated runs of the experiment, what would be the average value, the mean value of my outcomes? So let's think about this first with the dice game, and then we'll do the 3 coin flips. So you either get 10 or -1 for your winnings on any individual play. But if we did this over and over and over and over again, what would be our expected value? Would we like to play this game many, many times, or would we rather not play this game many, many, many times? And the expected value will tell us whether we should like to play this game a lot or not. So let's think about it. Well, let me give you a formula first for the expected value. The expected value of a random variable is going to be a sum of products. So we want to read this expression right here as a product. It's the individual value that the variable takes on times its associated probability. So we're going to form these products, and then we're going to add all of them together, and that will be my expected value. So let's look at this dice example and see why this might make sense to us. So if we just literally apply this formula to the dice game, the possible values of little y are -1 and 10. So we're going to multiply -1 by its associated probability, 5/6, and then we'll multiply 10 by its associated probability, 1/6. We add those together, we get -5/6 out of this first product. We get +10/6 out of the second product. -5/6 plus 10/6 is 5/6, or 0.83. So notice that the expected value is positive in this case. And what are the values of y were money values, and so this is a money value as well. This is actually going to be in dollars because -1 and 10 were in dollars. And so what this is telling us is that if we played this game many, 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 many times, we would expect to win 83 cents, 83 and a third cents on average for each time we played it. So if we have positive expected value, that means this is a game that we'd actually like to play a whole lot. If I played it 100 times, if I expected to win 83 cents more or less per time, I would expect to win about $83 over playing this game 100 times. So this seems like a very advantageous game for us to play. But now let's try to think about why this might make sense. 5/6 of the time, you're going to lose $1. You're going to lose a lot. But when you win, you're going to win much more than you lose on any individual play. And so 5/6 of the time, you're going to lose $1, but 1/6 of the time, you're going to win $10. And so in the long term, you're going to lose $1 5/6 of the time. You're going to win $10 1/6 of the time. And so if I played it, say, just 6 times, and I lost 5 times and won one time, I would have won 83 cents. And so, I'm sorry, I would have won, start again. If I played this game 6 times, I would have lost $1 5 times. I would have won $1 10 times. That would give me -5 for the losses, +10 for the win. So I would come out $5 ahead in those 6 plays. And so $5 in 6 plays is an average of 5/6 of $1, or 83 cents per play. Let's look at the expected value for the coin flip situation. This is just remembering the table that we formed earlier. So according to the formula, we're going to multiply 0 by 1/8, 1 by 3/8, 2 by 3/8, and 3 by 1/8, and add those together. And that's what we do. We're going to do that by hand in the next slide, but let's see how we could do this in R. So we can let R do a little bit of work for us. So remember, the C command allows us to enter lists. And so we're going to assign to the variable X the list 0, 1, 2, 3. And the variable probx, we're going to list the associated probabilities in the same order, so that 1/8, this 1/8 goes with 0, this 3/8 goes with 1, this 3/8 goes with 2, and this 1/8 goes with 3. So we can enter this into RStudio. We've entered those values into the variables. And now, if I just form the sum of x times probx, RStudio is smart enough to know that that means that we're going to multiply the corresponding terms together and then add them. We see that we get 1.5. And so this is 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. That gives me 1.5. Let's verify that arithmetic in the next slide. So if I multiply this together, I get 3/8 from this. I get 6/8 from this. I get 3/8 from this last term. So I get 0 plus 3/8 plus 6/8 plus 3/8, 12/8, which reduces to 1.5. So this formula, and let's again just take a second to think about this. If I flipped a coin, if I flip 3 coins over and over and over again, what this is saying is that for any individual set of 3 coins, I would expect 1.5 heads. Now, obviously, I can't have 1.5 heads in any one set of 3 flips, but what we're saying is if we count the number of heads overall, over many, many, many sets of 3 flips, that the average number of heads should be very, very close to 1.5. And if you think about it, that makes a little bit of sense. Our outcomes were 0, 1, 2, and 3. Our distribution was symmetric, though, and so it seems like the average should be right there between 1 and 2, or 1.5. The last thing I want to introduce in this section is the notion of standard deviation. And the formula here should remind us a little bit of the formula for standard deviation we addressed back in chapter 2. So we're going to take our expected value can be thought of as a mean. So x minus the expected values are going to be our deviations. We're going to square those deviations, and then we're going to add them up. But what we do first is we add the product of the squares of the deviations with the associated probabilities. And once we do that, then we take the square root. So there are certainly common elements with what we did before in computing a standard deviation. So remember, our expected value for the coin flip problem was 1.5. Let's work through that example. So if these are my values of x and my expected value is 1.5, here are my deviations: 0 minus 1.5, 1 minus 1.5, 2 minus 1.5, 3 minus 1.5. If I square the deviations, I get 2.25, 0.25, 0.25, and 2.25 respectively. And so the associated probabilities are right here for 0, 1, 2, 3. And so we're going to multiply 2.25 by 1/8, 0.25 by 3/8, 0.25 by 3/8, and 2.25 by 1/8. That's what this expression here is all about. It's taking the sums of these products. So I'm taking the sum of the products, and then I'm taking the square root of that sum. And if you do the arithmetic, I'll let you verify this on your own calculator, you get 0.867 approximately. So remember how we interpreted standard deviation before. It's sort of an average value of average distance away from the mean. Also, we expect most typical values to be within 1 standard deviation of the mean. So our expected value is 1.5. If we add and subtract 0.867 to and from 1.5, we get a number about 0.633 and 2.367. And so what we're saying is that typical values for x should be between 0.6 and 2.4. And 1 and 2 are the values that are between these two numbers. And so we say typically we should get 1 or 2 heads and 3 flips of a coin. And let's just recall that those two outcomes together would happen. One of those two outcomes together would happen 3/4 of the time. And that's not too far off from the 2/3 figure that we had in the previous chapter. One last thing for you to do, I want you to try finding the standard deviation of why the winnings in the dice game. So work on that. We will talk about it in class. So that's it for this chapter. We will continue on with chapter 4 on a couple of different examples of random variables in the very near future.